So here I am at the Buda River. A few things that we can do with river sampling include temperature. Temperature's pretty obvious. One important thing to know about temperature is the warmer the water, the lower the dissolved oxygen. Warm water dissolves less gas than cold water. Warm water also raises the metabolic processes of every organism in the river, causing more production of CO2 from respiration and decon. So that one's pretty obvious. To measure pH, I don't know about those of you who are teachers, but I'm kind of tired of calibrating pH meters. We're not paid by the hour. Get some universal pH indicator paper. The stuff is awesome, it's easy to carry, and if they drop it, you're out 16 cents rather than an entire electric probe. So pH paper. pH paper tells us a lot about runoff as well as acid rain deposition. Buda River, just so you know, is an amazing river. Our water quality is so good, that's one reason why one of the main industries we have here in Fort Collins are breweries. And yes, it is called the Buda River. So those are two things, but I'm also going to show you today how to sample some other things. Those things are going to include invertebrate sampling as well as dissolved oxygen. Now, the cool thing to see when you're doing river sampling is also recognizing when some place is a safe approach. Alright, here I am at the Buda River. Today's lesson is going to be on stream sampling and stream safety. I'm making this both for my students for the class, but I'm also making it for a bunch of teachers who are always asking me how to do better stream sampling methods. So I'm here at the Buda River. It's beginning of May, and this is one of the first things I want to show you. We look at this river. Hang on. And adjust it a little bit. If you look, this river is moving a little faster than walking speed. When you see a river moving this fast, this is at the point where you really don't want students in the water. First little bits of safety for river sampling are keeping your students and the river safe. We don't want to pollute the river with students, we don't want to lose students, and we don't want to end up with chemicals or debris in the water. And we want to bring all students back safely. So, first rule is with swift water. If the kids are going in moving water, you as a teacher should be standing on the shoreline counting heads. According to lifeguard protocols, you can't keep track of more than 8 to 10 people, which means you might have to either do chaperoning or you've got to communicate who goes in the water and how deep. Another bit of safety, pick an access point where it's easy to go into the river. So I picked this spot because it's a little slippery right here, but as you can see, it's a really gentle walk directly into the river. I also chose the slow section of the stream. Third bit of safety, get rid of your waders. I know they look cool. I know you feel like a teacher for those of you who love the waders. I know you feel like a scientist and a dorky biologist when you wear the waders as a student. As someone who did field sampling, we usually didn't wear waders. If the water was cold enough where you needed to wear waders, we generally found other ways to sample it. Waders are like giant anchors that will pull you to the bottom. Now, the other thing is with water. Once it becomes swift water, if you want to do full swift water sampling, you should get swift water trained, which means you're going to have to reach out to local EMTs that might have a swift water crew. Or my advice, find other alternatives such as this to show them the river. The reason why is once water is moving about 3 miles per hour, if you get deeper than your ankles in the water and a rock rolls over your ankles, you are going to drown. It's called impingement. Not even a life jacket will keep you up. So no waders, no going in moving water, find an easy access point. And also one other rule with water sampling is the rule in water sampling is if you're willing to throw it in the water, you're willing to lose it. So bear that in mind for environmental impacts as well as cost of materials. The good news is just not getting waders for those of you who are teachers is going to save you so much money. But we're now right here at the Buda River. It's just starting its spring crest. Within a week, where I'm standing, the water will be up to here. And at this point, the swift water has just started. It's kind of amazing right now. So, the other thing you need to talk about is what kinds of stuff you sample with rivers. Alright, so this is the spot of the river I chose to sample. Here are some safety things to look out for though. Once you start seeing rapids, when the water is moving faster than 3 miles an hour, that's what I talked about. It's going to be too fast for anyone to step in, deeper than ankle deep. The other thing to look at on rivers are your approach. This is the same for lakes and ocean sampling too. Approach means, is there an easy way in and out of the water? So if you look, this has a nice non-slippery transition to a path. It's going to be very easy to get to, but you also have to factor in mobility issues with students. This would be a section of the river that I would gladly choose to sample. For teachers, as I already mentioned, or you don't want to be sampling with you in the water and the students in the water as well. If the students are in the water, you're on land watching. One reason why you want to be watching is you never know when something's going to start working its way down the river. In this case, while I was recording about river safety, as you can see, a ridiculously large piece of woody debris is working its way down. Now this on its own, not dangerous, but if you had a group of students in the river with that, first of all, some of them would try playing with it. The other thing is if someone was not expecting it, they might try to rush away from it and trip and have problems in the river, or it might just knock them down. This is why you should have, if your students are in the river, you should be watching upstream. But as I've already mentioned, if the water is considered swift water, you should probably keep them out of the river. For myself, I would keep them out of the river if it's swift water. Today, this river has crossed the line to swift water. But now let's get into some more stuff about river safety. Now you've seen a safe approach. By the way, cross the river, that would be an unsafe approach. A safe approach has an easy walk into the water and an easy walk out. When sampling rivers, you're looking for signs of things that might be off, as well as signs of health, environmental indicators of anything. You could be looking at wildlife. Now, at the high school level, it's easy to work with, you're working with streams, with some of the basics. One thing is stream flow. Stream flow, the easiest way to do it is just mark off 2 points on the river, measure the distance, and see how long it takes things to flow across. Cool little detail. On the outside bend of a river, things will move faster than the inside bend. So if you're not sure where to go for stream sampling, go for the inside bend of the river because that's less likely to wash away students. For stream flow, I'm using flowers. There's no pesticides on them. My favorite stream flow meter is a orange. You pull the sticker off, it floats below the water level, it's not measuring airflow. But to measure stream flow, all you have to do is toss that in the river and then have someone keep an eye on it and see when it crosses a pre-established point. Cool thing with stream flow is the faster the water is moving, the more dissolved oxygen you have. The reason why is that increases air exchange, especially if you have rapids like I have. It's a tiny rapid. We'll just call it a rapid because it's not plural yet. Once you start seeing white water, dissolved oxygen is going up. And we can just measure the stream flow again. Yep, it's still flowing. Other things you can do are measure nutrients. The nutrients that impact plant growth that we always check are nitrogen and phosphorus. We don't test potassium because there's never been a major spill of bananas. I don't know why. But cool trick. If you're in salt water, only measure nitrate. Or if you're in salt water, only measure phosphates. If you're in fresh water, only measure nitrates. The reason why is in fresh water, phosphates are limiting. So every time you test for a limiting nutrient, it will read 0. The way you test for phosphates is with turbidity. And same thing in saltwater. Nitrates are the limiting nutrient, so they'll always read 0. So for that reason, you want to use other things such as turbidity. The easiest turbidity sensor is excellent. You fill a tube with water and you paint a black and white pattern on the bottom. You put a ruler on the side, it's called a Secchi tube, and it will tell you everything you need to know about turbidity. The murkier the water, the higher the nutrients. Nutrients can be high because of human reasons or natural reasons. When it's human caused, we call it cultural eutrophication. So those are some of the chemicals you can measure. Now let's say you want to measure dissolved oxygen. So you can go to the science lab and grab all of those weird sensors that never quite work. I actually don't like using electronic sensors. In field research, we started using them because they were highly maintained, highly tuned, but we always check them with a chemical titration. The dissolved oxygen test from Lamont, which is a Winkler titration. I'm not sponsored by Lamont, but this kit is amazing. For those of you who are teachers, it's like $50. The chemicals last far longer than a dissolved oxygen sensor. If you are going to buy a dissolved oxygen sensor, you want to get the optic ones. They last longer, but they're 3 times the cost, but they don't require calibration. But when you're using chemicals near the river, make sure none of the chemicals end up in the river. Remember, we're not supposed to make pollution in studying water quality. So this right here is a sampling bottle. I'm going to show you how to do the Winkler titration. And I'm going to fill it to the shoulder, which is right there. Now, as soon as your sample bottle filled, the scientist in each one of us, which makes poor choices, wants to shake the bottle. It wants to put it in its pocket. If you shake the bottle, you change the amount of dissolved oxygen. If you put it in your pocket, it warms up and dissolved oxygen goes down. So if you're doing this in the field, you want to do what's called fixing the sample right away. So the first chemical I'm going to add, just double checking the direction, is the manganese sulfate solution. There's your manganese sulfate. I'm going to add 8 drops. When your students do this, and if you're a student, you need to do this. Got to count it out. 1, 2, 3, 4, 5, 6, 7, 8. As soon as I put in the drops, you're going to have to tell them, do not shake the bottle, because the bad scientist in all of us wants to shake the bottle. Instead, you're going to go get the next bottle. It's got an awesome pirate on it, which means it's a bad chemical. It's alkaline potassium iodide with azide. Again, you're going to add 8 drops. 1, 2, 3, 4, 5, 6, 7, 8. So I've added my 8 drops of alkaline potassium iodide azide. And yes, I used to do this at the research lab. My research lab was on a boat. At this point, they can finally shake it. So you can shake it. Does not need to be shaken like a martini. And then you have to get the students to put the bottle down. At this point, the sample is actually fixed. So from this point on, you could actually do whatever you want with the bottle because it's not going to change. You've stopped all the science. What we've done is we've bonded iodine indirectly with oxygen. At this point, if they warm the bottle by putting it in their pocket or by putting it in a backpack to take it back to school, its dissolved oxygen is not going to go bad. If the little Timmy or, Jeff, who keeps killing houseplants, can't help himself and keep shaking it, it's not going to change it now. But what you want to do is you want to get the students to somehow, and if you're a student, you want to get these bottles motionless. You want to get them so what's called precipitate. But so in field research, when we do Winkler titrations, we might drop a carousel of water sample bottles up to about 2 kilometers to 3 kilometers deep. As soon as they got to the surface, we would fill, or we would fix the samples, meaning we'd add those first 2 chemicals. We'd also add the next chemical, but for the next chemical, I've got to wait till it settles down a little bit. The reason why you do that is that the last part of the titration takes forever. And even if you're a fast scientist, you want to have your samples preserved so nothing's going to change them. So when I usually do this with students, what I would do is fix the samples here, take them back to school. That decreases the chance of anyone putting chemicals in the river. For those of you at Poudre High School, the reason I don't take you to this river is it's too expensive and buses cost way too much money and I wish I could. However, I know you're familiar with the river. But once a sample is fixed, you form what's called a precipitate. A precipitate is a solid that settles out of a solution. And, oh, there's a cute duck coming. Oh my God. Check out the duck. Hang on one second. You see the duck? Look at it. Oh, look at that. That would not be a good stream flow indicator because it can move itself around. So, back to the sample bottle. with the help of the duct's distraction, if you look, do you see how the solid has formed and it's about a third of the way down? You want to get the precipitate at least a third of the way down. What's going to happen is half of your students are going to be unhinged and want to shake the bottle, and you're going to have to make them wait. What you're going to go next is you're going to grab sulfuric acid, like that. Ooh. What we're going to do is we're going to dissolve the precipitate. This I usually prefer doing away from the river. We're going to add 8 drops. And then we're going to shake it. And they want to shake it a lot. You can tell them, shake it like a Polaroid picture. If they like Outcast, you just got to shake it. Cool thing to note is the darker this is, the more it looks like a nice dark heavy beer, the higher your dissolved oxygen. But now, we have to actually titrate. So, what I'm going to do, and in the classroom I would have them do this over the sink. I'm carefully trained, but I would not recommend doing this in the field with your students. For students, we wouldn't do this in the field. I'm going to add 20 milliliters exactly without spilling any of this into the environment. There's meniscus at 20 milliliters. And I'm going to do a titration. One thing I like about this kit is it's got a safety cap, so, you know, someone like Alex is not going to spill it. The last thing we're going to do is we're going to start titrating. For teachers, this is where you got to guard them like hawks. This kit has a syringe, and if you look carefully, it's got numbers that go backwards. My first goal is to fill that syringe with this sodium thiosulfate, so that there's no air bubbles all the way into this pink titrator tip. This is where you get to play creepy nurse. So what you do is you put it in, invert the bottle, pull it down farther than you need to, and then you're going to do the creepy nurse flick of science. It's really creepy, especially when you're kind of got a pirate look going on today. Then you're going to go back and squeeze the air bubbles back in, and then bring the plunger back down to the 0 mark. Gotta do some more flicks. And if you look, I have filled the syringe to the 0 mark. This is where patience is going to be required by both students and those of you who are teachers. You're now going to put the creepy nurse syringe of science into the titrator tube. And my goal is to get this a very pale yellow. A good example of pale yellow is a yellow poster note. For those of you adults, a nice Pinot Grigio is the color you're going for. And I always tell my students you want to put in a few drops and do the swirl of science. The bad scientist in all of us wants to empty the entire syringe. Now, if you look, I'm already getting a paler yellow. If I put a background to it, you can actually see the color a little better, especially if I got some light on it. So with your students, and for those of you who are AP teachers, normally this isn't this fast. This is because I'm a total nerd who spent way too much time doing this. But I've achieved, it's kind of a Chardonnay, and I want more of a Pinot Grigio. If it looks like Pinot Noir, you've done something horribly wrong. So there we are at a pale yellow. You're going to take the syringe, and you're going to tell your students, do not empty the syringe. If you're a student, do not empty the syringe. Because we still need to add more. In this case, I've added 8. What that means is there's at least 8 units of oxygen per unit of water. And the units are in, I believe, parts per million. They are in parts per million because I read the directions. But we're going to put this down without emptying it. If you do empty it, you want to refill it to the 0 mark so you can avoid math. Now I'm going to make this blue. I'm going to do it by adding 8 drops of starch indicator. The starch is great because starch bonds with the oxygen. When it bonds with oxygen, turns blue and iodine. Sorry. 1, 2, 3, 4, 5, 6, 7, 8. If you're doing this with your students, my advice is have one person in charge of putting all chemicals back in the box perfectly so that you don't break as a teacher. Now that I've added the starch, as you can see, it has turned a nice, beautiful dark blue. Now, titration, I tell my students, is Latin for painfully slow. It's not. What you're going to do now is we're pretty close to the titration point. Your goal is to not make it clear. Your goal is to get a storm cloud or a Dementor in a bottle. So I'm going to add a few drops and swirl. Add a few drops, swirl. If you look, see if we can get some light on this one. Is there some better light here? We're going to move to a better light source. And that didn't help at all. So, sorry for the bad color, but we're going to add some more drops. Ooh, it's going clearer. You see that? Ooh. And that right there is called overshooting your titration point because I added too much. Now, with your students, if that happens, my goal for the first time they do a titration is that they see what titration point looks like. If you really want them to see the titration point, all you have to do is put some more of your original mixture in the bottle. And as you can see, I brought it back to a blue color. Now I'm going to refill the syringe and just add more sodium thiosulfate. Again, doing the creepy nurse flick of science. So let's try to get this titration again. Add a drop, swirl. Ooh, that was that close. Now it looks clear until you put a white background on it. If you put a white background on it and made better light, you would see a hint of blue in there. But so that's telling us the titration point somewhere between 8 and 10. I'm going to redo this and then give you the result. Okay, so I redid the titration. Turns out dissolved oxygen was reading at about 8.6 units of sodium thiosulfate that I added. Sorry, 9.6. That means the dissolved oxygen of the Poudre River today is 9.6. With your students, if you have access to river, what you can do is take water samples every day, fix them, and see how the dissolved oxygen changes as the river crusts, because invariably it will go down. But next I'm going to show you how to measure for invertebrates. So this is something where you want to do it when the water is moving a little slower. But since there's not students watching, and also because I found a section of the river where right here is actually a little eddy where it's slowing down, I'm going to pull out some rocks to look for invertebrates. So, this is one of the easiest ways to do invertebrates. If I weren't locked out of the school right now because of a freaking epidemic, I'd get you a dip net and show you how to use a dip net. You put it in the water and you jump on and kick up the ground upriver of it. So just looking at these rocks, I can see some pretty awesome things. Right here, if you look right there, we have a baby mayfly. We're seeing actually a change in invertebrates in this river because of the river's restoration. A mayfly means you have super good water quality. For those of you who like to ice fish, or fly fish, that means this is a good fly fishing river. Let's see what else we got on here. So once again, mayfly, right there. Oh, it's such a cute mayfly. We have some tiny leeches. Those are not a good indicator of water quality. But just by seeing the mayfly, we already know we got good water quality. And there's even a little caddisfly on there, but not a good one. So after you're done sampling, looking at your rocks, make sure you return the invertebrates to the river. Here's another rock. Not much on this one. Okay, so here's another one, and this time we've got some snails on here. So, snails are usually found with slower moving water. We got some Tubifex worms. Aww. And what I didn't see here are some other things, but as soon as you see mayflies, you know you got good river quality. So I'm going to give you a montage of pictures showing you some other ones showing good water quality. Mayflies, or juvenile mayflies and caddisflies and stoneflies are kind of the Gucci of water quality. That means you have really good water quality. So I've returned them all to the river, and now it's time to go home and walk my dog. And just so you know, all my chemicals went into a waste bottle that I'm taking back with me. All right, this is to help walk you through identifying different freshwater invertebrates. It's with the help of my professor, Dan Young, from my entomology class in college. First group we're going to go over is Odonata, which includes dragonflies and damselflies. Dragonflies can actually live 7 years underwater in their immature stage as a naiad. The way to recognize them is they're bigger and they have no gills on their tail. They also, both dragonflies and damselflies, have a really cool jaw, so I'll show you in a second. So here's a dragonfly. They can be longer, skinnier shaped. They can be big and scary, but they have this weird bottom-grabbing jaw you can tease apart with a needle called a raptorial labium. Damselflies are smaller, and if you hold them in a little puddle of water in your hand, they're really cute swimmers. They kind of writhe around like little tiny sharks. Those three things on the back are the gills. Hellgrammites are really scary looking, but they're a sign of relatively good water quality. So here's Hellgrammites in different stages. The way you recognize them is they've got big pinching mouth parts that technically aren't supposed to pinch you, but they've pinched me and they kind of hurt. But caddisflies build cute little houses out of leaves, sand, and twigs. In college, we actually had to identify these for some of my research, and you identify them by what they use to build their houses. And so they look like little tubes, but you can pull them out. Mayflies and stoneflies are the Gucci of water quality, and they're the hardest ones to tell apart. So I'm going to show you the trick I learned from Dan Young. Mayflies have gills on their abdomen, so he always said, look for a hairy belly. It also looks like they were flattened with a rolling pin. So this is how they look, but if you hold them in a little puddle of water in your hand or in an ice cube tray, you will see the gills float off the side, and that's what I mean by they have a hairy belly, even though those are gills. Stoneflies have hairy armpits because the gills are where the legs attach to the body. They also have big scales in the back called scutes. So there you can kind of see the hairy armpits. To make it easier, here's a lab drawing. So if you see hairy armpits, you've got stoneflies, and if you see a hairy belly, it's a mayfly. But both are indications of really good water quality. And that's how you do the water quality index.